Today we want to upgrade our double integrals in polar coordinates to triple integrals in other coordinates. The concept here is that we're trading one of our variables, or we're turning one of our distance variables into an angle variable. So in rectangular coordinates, x and y both represent distance. Rectangular coordinates are great because the intersection of two intervals will just be a rectangle. Things are different in polar coordinates. In polar coordinates, we have locations described by r and theta. So a distance and an angle. The intersection of two intervals in polar coordinates will be the sector of a circle, possibly with some missing if r does not start at 0. We want to be able to set up double integrals. One of the pieces of a double integral is the dA, where the dA represents area. If x and y are both distance, then dx dy will give us an area like we want. But d theta is an angle and dr is a distance. So we need to have that extra factor of r from the arc length formula to turn d theta into a distance so that dA can be an area. So that's what we want to think of moving forward into triple integrals, because we're going to go from rectangular coordinates where x, y, and z are all distances and start replacing some of those variables with angles. So here we have rectangular coordinates. And here we have polar coordinates. Also remember that sometimes one set of coordinates is better for the given situation than another set of coordinates. We can describe circular stuff with rectangular coordinates, but I mean, it's right there in the title. Rectangular coordinates, not going to be good at describing circular stuff. Polar coordinates, very good at describing circular stuff. Not so good at describing rectangular stuff, or it's just messier. All right. Let's add another variable. In triple integrals, we're going to have 3 coordinates. So rectangular coordinates in R3, we're just taking the rectangular coordinates that we had in R2 and slapping a z-axis onto it. So those are the rectangular coordinates that we started with. We're describing a plane, and we're sticking z onto it. So that a point in space here will have an x coordinate, a y coordinate, just like before, and then we'll have a z coordinate. So that the point x, y, z will just be right above the point x, y, 0. We're just taking the x, y coordinates that we're familiar with and putting a z coordinate, a z axis perpendicular to it. If instead of starting with the xy plane, we start with polar coordinates. If we start down here instead with polar coordinates, And describe, say, this point as r and theta. We turn polar coordinates into cylindrical coordinates. Which one's which? I use orange for r first. Theta, rotating positive x-axis. If we take polar coordinates and stick a vertical axis on it, a z-axis, these are called cylindrical coordinates. And all we're going to do is take polar coordinates, r, theta, and 0, and stick a z-axis. Rectangular coordinates is R3, is just the XY plane and a perpendicular Z-axis. In polar coordinates, we just take the R theta plane and attach a Z-axis to it. So cylindrical coordinates in R3 is just polar coordinates plus Z-axis. Same thing that we did in rectangular coordinates in R3. We just took the XY plane and stuck a Z-axis on it, perpendicular to the XY plane. I know some of you have been through linear algebra, and it doesn't always have to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. It could be any three vectors that we want, any three linearly independent vectors. So it doesn't actually have to be perpendicular. But when we're making coordinates, we want nice perpendicular coordinates. That means it's very easy to upgrade our double integrals to triple integrals. For our rectangular coordinates, we can describe a triple integral over some solid W of a function of x, y, and z, dv. Now, dv is some small piece of volume, some small chunk of W. It's like a little cube in W. If we make a triple integral in rectangular coordinates, then we can break the dv up as a dx, a dy, and a dz. If we are working in cylindrical coordinates, then d theta is still an angle and not a distance. So in cylindrical coordinates, our function will be r, theta, and z. We have the same problem that we had with polar coordinates. Theta is an angle, not a distance. R and z are both distances. They are okay. But d theta on its own is not an angle. Sorry, is not a distance. dr is a distance, and dz is also a distance. Fortunately, because cylindrical coordinates are just polar coordinates plus the z-axis, the same r that we use to turn d theta into a distance in polar coordinates is the r that we can use to change d theta into a distance in cylindrical coordinates. So that factor of r makes d theta a distance, so dv can be a volume. And it comes from the same thing. We have some small change in angle. To make that angle a distance, we need to know how far from the pole we are. How far from the pole do we want to take that little change in angle? That makes an arc length. So even though it's slightly curvy and not quite a rectangle, if we make d theta small enough, it'll be very close to being just a straight piece. Any questions? If you recall, we had described a sphere of radius, I think I picked capital R because I always do that ill-advised thing. So we found the volume of a sphere. We wrote a triple integral for the volume of a sphere. And it was very inconvenient. We ended up at a place where we were going to have to do some trigonometric substitution. Let's revisit that volume of a sphere with a triple integral in cylindrical coordinates. So if you recall, we were dealing with the sphere. I can't remember if I used R for a radius or I used a number, but today we're going to use a radius of 3. I think I did the other order last time, but just switch the Z and the X. So if you recall, we had set up this triple integral to describe a sphere. And if we replace the function f of x, y, z with 1, this triple integral will tell us the volume of the sphere. The problem that we ran into is that after the first integration, integrating dz is no problem because it was just 1. Then we had to integrate 2 square roots of 9 minus x squared minus y squared with respect to y. And then all of a sudden, we had to do trigonometric substitution and we didn't want to. So let's redescribe our sphere, but in cylindrical coordinates. The z is the same. If we're going to switch from rectangular to polar coordinates, I'm going to need to translate x and y into r and theta. So now if we want to describe the sphere, instead of the dz can work out this similar fashion, but instead of saying not x squared plus y squared plus z squared equals 9, I can replace x squared plus y squared with r squared, where r is in the r from polar coordinates. So in cylindrical coordinates, when I need the upper and lower bounds on z, I just have plus or minus the square root of 9 minus r squared. So I still have to describe with this plus or minus square root part, because remember, z works the same way that z works in our rectangular form. So we're not surprised that z still wants this plus or minus square root business to describe the bottom and the top of our sphere. But all the r is, all we need is the r for the z coordinate. We don't need an x and a y. So now if we're going to set up a triple integral, no, I set up dz first. And so z will go from minus the square root of 9 minus r squared to the positive square root of 9 minus r squared. Now, in this case, when we look at the top view of what we're trying to describe the region that we're going to plug into these to get these z values. Now we're looking top down at a circle, and in cylindrical coordinates, a circle in the r theta plane is just a set of integrals. So d theta will just go from 0 to 2 pi. And for dr, r just starts off at the pole and goes out to the radius. We still need a factor of r to turn d theta into distance. D theta is still just a change in angle, but if I multiply by the radius, now r dz, d theta, dr, all that together is a dv. Any questions on the setup? What's r between? What's theta between? What's z between? The z is just the bottom minus square root and the top plus square root. If we look at this from the top and we want to describe a circle of radius 3 in polar coordinates, r goes from 0 to 3 and theta goes from 0 to 2 pi. So here's theta at 0 and theta equals 2 pi. Just go all the way around. Starting off at the pole, that's where r is equal to 0. And at the end of the radius of the circle, that's where r is equal to 3. In polar coordinates, a circle is just the intersection of two intervals. So if I replace the function f of r, z, and theta, r, theta, and z with 1, we know that this should give us the volume of the region over which we are integrating. The r is not part of the function f, it's part of the dv. It's still something that we have to integrate, but it's part of the dv. So when we integrate, the first integration that we do is the dz integration. Here we are describing our region, which is just going to be the circle of radius 3. The integral of r dz is going to be rz. And we'll evaluate from negative square roots of 9 minus r squared to plus square root of 9 minus r squared. At this point, if we don't look ahead carefully, we might think, oh, is this not just going to lead to more trigonometric substitution? Why is this not going to lead to more trigonometric substitution? I'm about to plug in 9 minus r squared. It's going to be sitting in a square root. There's going to be 2 of them. I'm going to have a 2 square root of 9 minus r squared. And I just said, we're still going to be able to avoid the trigonometric substitution. Why do we get to avoid the trigonometric substitution? We can just do a plane substitution. We have already done the trigonometric substitution when we switched polar coordinates. We had already done our trigonometric substitution. That's why we don't have to do a trigonometric substitution here. We can get away with a plane substitution because of this extra factor of r. So we can just say w is 9 minus r squared, and then dw is minus 2r to r. I've even got the 2. Excellent. So I guess we'd have a minus dw is 2r to r. So we're just integrating minus w to the 1/2. So the integral of minus w to the 1/2 is going to be 2/3 w to the 3/2. And so we're going to have a minus 2/3 9 minus r squared to the 3/2. Now looking at what we've ended up with. Now we're just integrating with respect to theta from 0 to 2 pi. This is constant with respect to theta. We're just going to be multiplying by 2 pi. This is where that this is where the 4/3 shows up. This is where pi shows up. In rectangular coordinates, we needed to do some trigonometric substitution because we needed pi to show up, and pi is only going to show up when we're plugging in these whole numbers if we have an arc sign running around. So that's what's going to happen in our trigonometric substitution version of things. But now we're just integrating this function of r first over the interval from 0 to 2 pi. And then we'll have to integrate with respect to r. Any questions? So in this case, it looks like we just put the trig sub off. Bummer. Any questions? I don't want to do the trigonometric substitution. I know it's all your y'all's favorite integration method, but I don't want to do it. I know it was a bit of a rug pull. It's like, oh, look, we don't have to do the trigonometric substitution yet. So, bit of a rug pull. Dick move on my part. Every friggin' semester, same thing. Your teacher is a dick. Fortunately, there is another Yoda moment. Another Skywalker. By the way, that's not a spoiler. That movie came out in like 1983. There's a statute of limitations on that shit. Darth Vader is Luke's father. That was 81. If you have not seen The Empire Strikes Back yet, you don't get to have that. Now, if there's a movie that came out this year, that like something happens in Quantumania, you probably shouldn't say anything because it's like still in theaters. That's still within the statute of limitations. So their spoilers are still available. But like in 40 years, you can't be like, oh, hang on, man, I haven't seen Quantumania. You just say, tough shit, dude. This is what happened. You know what I mean? Yeah, I think. Yeah, we know about like Star Wars. We know like I don't know. Like I mean any M. Night Shyamalan movie. Incidentally, if you watch a movie and there is a twist and you tell people that you won't believe the twist, you already fucked up. It doesn't matter that you didn't say what the twist was, just the mere mention that there is one means you spoiled it. It doesn't matter if you said what it exactly was, but you see trailers do this all the time. You won't believe the twist. I'm like, oh, well, now I will. Now I will. Because I go, oh, this must be the twist that you were talking about. Not that I really care that much about spoilers, but.
I think everyone is like Jack inside.
Right.
But there's a thing that Mary and Captain actor survived.
It's the same dude. Ah, a little bit of a Count of Monte Cristo shit going on. All right, I'll buy into that. It depends on the theory.
Yeah.
Like you can't let Mark Ruffalo like give any interviews because he's like joking. He's like, "Oh, everybody dies." I'm like, "Oh, well, half the people." Yeah. Yeah. So. Yeah, you got to leave all that. So if you've read the comics, it's probably going to be different. So just tell people that you've read the comics, and then we'll all stipulate that you have superior knowledge.
Yeah.
And so defense prosecution stipulates.
But no matter what?
Yeah. Anyway, that's gonna do it for today. I will see you all on tomorrow. Everybody have a good day. And we'll do spherical coordinates. Spoiler alert. See you tomorrow.